So I'm going to start by talking about the chain rule today. So you guys remember the chain rule from Calculus 1, right? So we're going to generalize that now to functions of more than one variable. So let's say that I have some function of x and y, but then I have a function inside. So I'll just make something up right now. So if I have an expression like this, where I have functions inside of f, we want to know, well, all right, so we want to know how to compute, say, the partial derivative of such an expression, say, like with respect to s or with respect to t. Okay? So the chain rule gives us sort of like a formula for computing derivatives of things of this nature. So in general, if I have a function f, which I'm thinking as a function of two variables x and y, but then let's imagine that I replace x and y with some other functions. So let's say I replace x with a function of s and t, as I started to do in this example of sorts here. And let's say y is also some function of s and t. So we want to know how to compute the partial derivatives of f with respect to s, and then also with respect to t. So what I'm going to do right now is I'm going to write out just sort of what the formula will look like, okay? So you sort of remember the chain rule from Calculus 1, it was like do the derivative of the outside function, then times the derivative of the inside function. You guys remember that? So it's a little bit similar. So we would do the derivative of the outside function, which is f. And then we times the derivative of our inside functions. Now we have two functions on the inside, x and y. So what we have to do is we have to do the derivatives with respect to x and y. And then multiply them together, and then we have to add all of them up, okay? So this would be to get the partial derivative of f with respect to s. And then to get the partial derivative with respect to t, you kind of follow the same format. Only difference is when you get to x and y, you want to differentiate with respect to t. So this is one instance of the chain rule. Okay. And you guys have sort of like a device for sort of memorizing how the chain rule works. So you guys draw like a sort of a tree diagram of sorts, is what I've seen, okay? So I'll just kind of illustrate the tree diagram. Okay. So I start with the function on top, so I'm going to write f on top. And then in this example that I started, f is a function of two variables, x and y, okay? Then x and y themselves were functions of s and t. Okay. So in order So here we were talking about getting the partial derivative of f with respect to s. So the idea is if you look at your tree, what you want to do is look at all the paths going down from f to s if you want to do the partial with respect to s. And so what we did was we had f goes down to x and then down to s. So that's referring to this part here where you have to do partial f with respect to x and then times partial x with respect to s. Okay? And then likewise, we also had this path here going from f to s. So that signifies needing the partial f with respect to y, and then times the partial of y with respect to s. Okay? So are you guys kind of familiar with the tree diagrams and how to use it to help you in writing out the chain rule? Yeah? Okay. All right. Now, I gave a specific example where f was a function of two variables, and then x and y were also functions of two variables. I can generalize that to like higher numbers of variables. You can still figure out the chain rule if you draw the appropriate tree diagram. Okay. So before I do that, I just wanted to do like some explicit examples. So let me make up an actual function of x and y right now. Let's do something like x squared y cubed, okay? And then let me make up two functions of s and t for x and y. Let's say x will be s squared minus t squared, as I did in my example, and I'll do y as 2st for the moment, okay? And so let's try to see what the partial derivative of f with respect to s would look like if I were to follow the chain rule written up here, okay? So according to the chain rule, it should be the partial derivative of f with respect to x, and then times partial x with respect to s, and plus partial f with respect to y, times the partial of y with respect to s, okay? All right, so let's just compute all of these partial derivatives. So the partial of f with respect to x, what would that be? Anyone?
Respect to what? S?
Yeah, partial of f with respect to x, so the first term here, what would that be?
Oh.
2x.
Mhm.
1 and 3.
Yeah.
Yeah, okay, good. What's the partial of x with respect to s?
2s.
Okay. Let's continue. So now we need the partial of f with respect to y.
3 to the x squared y squared.
Okay. And times the partial of y with respect to s.
Negative 2t.
Partial of y, yeah.
Oh, y, 2t?
Yeah, 2t, yeah. Okay. Okay, now right now, the answer might look a little bit strange because you have x and y and s and t everywhere. So if I want my answer only in terms of s and t, then what I also need to do is I need to then plug in for x and y these expressions. Okay? So if I plug in s squared minus t squared for x, and then if I plug in 2st for y, then this would be the chain rule in terms of s and t. 3, and then I'm going to have x squared times y squared, and then we have times the 2t at the end here, okay? All right, so do you guys see how the chain rule works in this example? Okay. So then we had 2 times x, this was the y cubed, right? And then here, this was like 3x squared, then times y squared, and then times the 2t, all right?
Oh, so it's just like plugging in.
Yeah, plugging it in, that's right, yeah, okay. All right, so then let's just also compute the partial f with respect to t. Okay, in this example. You could simplify this, but of course, I'm not going to. I just wanted to illustrate the chain rule, all right? So partial f with respect to t, using the chain rule, so it's partial f with respect to x times partial x with respect to t. And then we're going to do partial f with respect to y and partial of y with respect to t. Okay? So let's plug in all of our numbers. So partial f with respect to x, that was 2xy cubed, right? Now this time we need the partial x with respect to t. So that should be negative 2t, right? And then the partial f with respect to y, or sorry, f with respect to y, it was the 3x squared y squared. And then the partial of y with respect to t was 2s. All right, is everyone good with that? Okay, all right. And then again, if you need to write it all out in terms of s and t, then again, just replace x with s squared minus t squared, and replace y with 2st. Okay? And for my purposes, I'm just going to leave my answer like that. Okay, any questions? Okay, all right. So let me look at another example now. So again, I'm just going to write out a function for x and y. This time, let's do something like x squared plus y squared. And let's see what happens if we write x and y in terms of polar coordinates. Okay? You guys remember what polar coordinates was? You should, right? Okay, yeah. All right. So then, since x and y are functions of r and theta, we can think of f as a function of r and theta. And then let's try to compute the partial derivative of f with respect to r. Okay. So using the chain rule, so it's the same as what we had before. I just need to use r and theta instead of s and t. All right. So I'd have like a partial f with respect to x, and now I'd have partial x with respect to r. And then we do plus partial f with respect to y times partial of y with respect to r. Okay? All right, so we'll plug everything in. So the partial f with respect to x, what is that?
2x.
Partial x with respect to r.
Negative r sine theta.
With respect to r.
Oh, it would just be cosine theta.
Yes, okay, very good. And then partial respect to y would be
2
okay. And then partial of y with respect to r. All right, good. All right, and so then again, sub in x and y. So we'll replace x with r cosine theta. And it's times another cosine, so I'll write it as cosine squared, okay? And then likewise here, replace y with r sine theta. And since we're multiplying by an extra sign, I'm going to write sine squared. Okay? Yeah, so if you factor out the 2r, cosine squared plus sine squared equals?
1.
Yeah, so it would just be 2r. Okay. Okay, let's also do the partial f with respect to
So like, would
theta.
that be the answer to what?
Yeah, for the partial f with respect to r.
Oh.
Okay. Let's look at the derivative with respect to theta as well, all right? So chain rule is partial f with respect to x, and x with respect to theta, and then plus the partial f with respect to y, and then y with respect to theta. So now we're going to get 2x, and then here dx d theta. So now it's going to be minus r sine theta. Okay? And then here we'd have, this is 2y, and then dy d theta would be, this time r cosine theta. Okay? So if I do the same thing as before, so sub in x to r cosine times minus r sine. Then next, this would be 2r sine, and then times r cosine. Okay, so what happens if we add all that up? Cancels, all right. So the answer would be 0, okay? All right, now this is a good example to actually kind of check that our answers are correct, all right? Okay, so here I want to make an observation. So just now we computed our partial derivatives using the chain rule. Now, in theory, there's another way that we could have found the derivatives. What we could have done is, starting with f, what we could have done is subbed in for x and y directly first. So then this would be like thinking of f as a function of r and theta right now. Okay. Now if I plug in directly into f to start with, and then if I simplify this expression, how would this simplify?
To r.
Not just r?
To
Not 2r. So when you square r cosine, what would that become?
r cosine.
Well, yeah, so we have r cosine,
Oh,
and
cosine
then
squared.
r squared. Yeah, it gets squared, right? So it'd be r squared cosine squared, right?
Oh, okay, squared.
Plus, yeah, r squared sine squared.
Oh, so it'd just be r squared.
Yes. Really? Okay. Okay, so then what we have is f in terms of r and theta is just r squared. So if you look at that, what's the partial of f with respect to r?
2r.
Okay. What's the partial of f with respect to theta?
0.
Yeah, because it's just I guess r squared would be constant with respect to theta. So then that agrees with what we found when we used the chain rule. Okay? So in your problems, they'll probably ask you to specifically use the chain rule, meaning that you'd have to compute the derivatives in this way. Okay? But in theory, you could also plug the functions into your first, and then get the partials. And perhaps you could maybe use that to double check your answer at least.
What would you recommend to do?
Well, again, I assume the problem would say, like, use the chain rule, meaning you'd have to do it this
You
way.
have to do it.
Right. Because I guess, like, this doesn't use anything, like, special. They probably want you to use the chain rule, so, okay? But I just wanted to show you that you can sort of confirm your answer by doing that kind of thing. Any questions about that? Okay. Okay. So just wanted to note that I can apply the chain rule to situations with more than one variable. So say like if I had a function f, but let's say it's a function of 3 variables, x, y, and z. Okay? And then let's say that like x and y, or sorry, x, y, and z, they might be functions of maybe u, v, w. Okay? Okay. So if you want to compute now the partial of f with respect to u, okay, so here we have 3 branches going down to u. That probably looks awful, but so in order to get the chain rule, I would want to do, going down this first branch, the partial of f with respect to x, and then times the partial of x with respect to u. So this is kind of similar to what you've seen before. All right, so then next, in the second branch, I have f to y to u. So I would need to do partial of f with respect to y, partial of y with respect to u. And then my third branch from f to z to u, I would need to add partial of f with respect to z times the partial of z with respect to u. Okay? And I don't think you'll get anything too complicated, but in theory, you could have like a really complicated situation. But as long as you draw out the tree diagram, you can still figure out what the chain rule should be. Okay? All right, so you guys kind of understand how to use the tree diagram to get the formula. So I'm not going to write it up, but just want to kind of illustrate. So you could do something like this. Like how I had before. But then you could have like u and v and w are now functions of s and t. So in theory, your tree could have like multiple levels to it. Okay? And then here I might want to do like, okay, partial of f with respect to, let's do with respect to t. Okay? So I'll probably write part of it out, but not all of it out because it's a little bit long. But here's one branch where I have from f to t. So what this tells me is I would need partial of f with respect to x, then partial of x with respect to u, and then partial of u with respect to t. Okay? Can you guys see that? Okay. And then I'll just write out one more. So here's another branch from f down to t. So I would do this one next. So then next I'd have partial of f with respect to x, partial of x with respect to v, and then partial of v with respect to t, and so forth. So you could write out the entire formula if you were to go through the entire tree, okay? So I'm not gonna write it all out because it's very long, but I just wanted to show you you can do more complicated situations, all right? Any questions about that? Okay. Okay, let's do a couple questions. Okay, let me do this question. Okay, so let's say I have a function of x and y. And then again, let's just assume x is a function of s and t. Likewise, that y is a function of s and t. Okay? Now, this time I'm not going to give you what all these functions are, but I'm going to give you some information about them. Okay, so let's say we're given that x evaluated at 1, 2 is equal to 5. Okay? Let's say y evaluated at 1, 2 would be equal to negative 2. Now let's say we are also given the partial derivatives. So x with respect to s, also evaluated at this point 1, 2. Let's say that's equal to 2. The partial derivative of x with respect to t, evaluated at this point, let's say that's given to be 5, okay? Let's say the partial of y with respect to s, evaluated at this point, let's say that's equal to 1. Partial derivative of y with respect to t, again at this point 1, 2. Let's say that was 3, okay? And then let's say just a little bit more. We also have some information about the partial derivatives of f and with respect to x and y, okay? So I'm going to be given the partial derivative of f with respect to x I'm going to write at 1, 2 is equal to 4. Partial derivative of f with respect to y at 1, 2. Let's say that's equal to negative 3. Okay. Also, partial derivative of f with respect to x at the point 5, negative 2. Let's say that's equal to 1. And the partial of f with respect to y evaluated. Actually, I don't want all this, do I? Actually, no, let me erase this. Actually, no. For this problem, that's all I want to do, okay? So we're given all of that information. And then actually what we want to do is we want to find the partial derivative of f with respect to x. Yeah, at this point, 5, negative 2. And then I want to find the partial derivative of f with respect to y at the point 5 and negative 2. Okay? All right. So let's just write out the formula for the chain rule first, and let's just take a look at that formula, okay? So according to the chain rule, we could say that the partial f with respect to s, it should be partial f with respect to x times partial x with respect to s, right, and then plus partial of f with respect to y, and times partial of y with respect to s. So one of the things that I wanted to point out with this example is when we look at this formula that I've written down for the chain rule, right? One of the sort of downsides to our notation is that here I'm not indicating that at what point all of these are being evaluated at. So this example is sort of designed to get you to realize some subtlety there, okay? So let's say if I look at this expression right now, let's say I want to evaluate it now at this point. Let's see here. Okay, and I'll note one thing up here. So I guess what I want to indicate or emphasize is when I write down x of 1, 2 equals 5, since x was a function of s and t, so what I want to emphasize are these are like values for s and t, right? So we're saying like st is 1, 2. Okay. And I'll tell you what, let me use a different color since I want to emphasize this. Yeah, so here I'm emphasizing that the values of s and t that we're working with are 1 and 2. Okay, but over here, right, when I had the partial derivatives of f with respect to x and with respect to y, okay? F is a function of x and y, so these partial derivatives are actually looking at x, y values, okay? So that's kind of a subtlety, but these points are referencing different variables. The 1, 2 is actually referencing s and t, but down here, this x and y are actually referencing, or sorry, this 5, negative 2 are actually referencing x and y as opposed to s and t, okay? Does that make sense to you guys, what I'm trying to say? Okay. So similar to when we did it up here, when we did the partial with respect to x, it was in terms of x, not in terms of s and t or whatever, okay? Okay, so then let's see how this problem will work. If I try to evaluate when, when s and t are 1 and 2, okay? Okay, so that's going to be the partial of f with respect to x. And I'm going to write it like this for now. And I'm going to do partial x with respect to s. So here, this is in terms of s and t, so I'm going to plug in our points 1 and 2 for s and t. But partial of f with respect to x and y, those are in terms of x and y. So it will actually be incorrect for me to plug in 1, 2, which is why I'm leaving them blank for the moment. Okay? So what I need to do is I need to make sure I'm not plugging in my values of s and t, but my values of x and y. Okay? So the idea was when s and t are 1 and 2, we know that x is equal to 5, and we know that y is equal to negative 2. Okay? So that means that for my x and y, I need to plug in the point 5, negative 2. All right? And likewise here, for x and y, I need to plug in the point 5, negative 2, not the point 1, 2, because that's for s and t. Okay. All right, so does that make sense to you guys? All right. So then if we plug in the numbers that we were given, oh, I'm sorry, I miswrote this. This should be S and T. Okay. So then the partial of F with respect to S at 1, 2, we're saying that's equal to 4. Now I don't know the partial of F with respect to X, but that's what I'm looking for. Now partial of X with respect to S at this point 1, 2, that was given to be 2 in our problem. And then likewise here, the partial of F with respect to Y. So again, that's one of the things that we were looking for. So I'm just going to have to copy it down. But I do know that the partial of Y with respect to S was equal to 1. Okay? So I plug in the numbers that were given, that gets me one equation. Now, I have two unknowns, so I needed a second equation in order to solve for my two variables, or my two unknowns. So let's look at the partial of F with respect to T. Okay? So using the chain rule, I would have partial of F with respect to X, partial of X with respect to T, and then partial of F with respect to Y, times partial of Y with respect to T. Okay? So then if I try to plug in evaluate when S and T are 1 and 2. So it's going to be similar. Okay. So we're going to have partial of F with respect to X. Now when S and T are 1, 2, again, X and Y should be 5 and negative 2. And then we have partial of X with respect to T at this point. And then next we'd have plus partial of F with respect to Y. Again, X and Y should be 5 and negative 2 when S and T are 1 and 2. And then partial of Y with respect to T at the point 1, 2. All right. So we'll plug in all the numbers that we have again. So partial of F with respect to T at the point 1, 2 is negative 3. So we're looking for the partial of F with respect to X. Now the partial of X with respect to T, that's given to be 5, all right? And then partial of F with respect to Y. And then partial of Y with respect to T, that was given to be 3. Okay? All right, so then what happens is we have these two equations, all right? Now, just so I don't have to write as much for now, let me just sort of abbreviate. I'm just going to call this A and I'm going to call this B, just so I don't have to write out so much, all right? But essentially, this gives me an equation. I have 4 equals 2A plus 1B. And then kind of similar, this second equation would be like negative 3 is like 5A, right? This is A. And then it would be like plus 3B. Okay? So then I'll try to either substitute or try to combine these equations to solve for A and B. Okay? All right, so I'll tell you what I'm going to do is I'm going to take my first equation and I'm going to multiply it by 3. So I'm going to get 12 equals 6a plus 3b, okay? And then here's my second equation, negative 3 is 5a plus 3b. So what I'm going to do is I'm going to subtract these equations. So I'm going to get 12 plus 3 is 15. And then on the right-hand side, you'll get a, okay, after you subtract. So then we solve for a. So that tells me that the partial of f with respect to x at the point 5, negative 2 should be equal to 15. Okay? And then to solve for b, let me just go back to equation 1, where 4 is 2a plus b. And if we just substitute a, you can solve for b. Should turn out to be negative 26, it looks like. So then b was the partial of f with respect to y. So therefore, we will get this as negative 26. Okay? All right, any questions about that? So the only thing that I really wanted to emphasize is just that in the chain rule, these partial derivatives are evaluated at an x and a y, not an s and a t. So sometimes you need to be careful about that. All right? Okay. All right, so now let's talk about something else. I'm going to talk about the gradient vector. Okay? So if I have a function of x and y, the gradient of f, we denote it with this symbol. It's an upside down triangle and then f, all right? So the gradient of f, it's equal to the vector of partial derivatives of the function f. And now I'm going to write my partial derivatives using this notation, okay? If I want to emphasize the point that I'm evaluating at, I could write it like this. Okay, so that's all the gradient vector is. It's just a vector of all the partial derivatives. So it has some significance. So I'm going to talk about that pretty much for the rest of the review. Okay, so the first thing I want to note, now that I've introduced the gradient vector, that's sort of a special case of the chain rule. Okay? So let's say that I have a function of x and y. And this time, let's assume that x is just a function of t, and that y is just a function of t. Okay? So then, if I want to compute the partial derivative of f with respect to t, So the chain rule would tell me it's the partial of f with respect to x times the partial of x with respect to t, and then plus the partial of f with respect to y, and times the partial of y with respect to t. Okay? Okay, now, notice that this expression here, it kind of looks like a dot product between two vectors, right? So it looks like a dot product between the partial of f with respect to x and the partial of f with respect to y, with the vector x prime dx dt, y prime dy dt. Okay? Can you guys see that? I'm switching notation with my derivatives that you guys can follow. Okay. Okay, so if I let r of t denote the vector of x and y. So as you guys know, when we were studying curves, the derivative would be x prime, y prime. Okay. So then what I could say is I could write this dot product as this is the gradient of f, right? And this is dot product with r prime. Okay. So writing it out a bit more explicitly, this is saying that the derivative of f of r of t, which I'll write as x of t, y of t. Yeah, but I'll note the inside is just r of t. Okay. So the derivative of this composition is equal to the gradient of f evaluated at r of t, and then dot product with the derivative r prime of t. So this is like sort of a special case of the chain rule. Okay. So it's a special case where x and y were a function of only one variable. And in that case, we can express the chain rule in terms of the gradient vector. All right, so any questions about that? Okay. So there's one. So I went over this because it leads us to a very important fact about the gradient vector. Which I'm going to talk about now. So I'm going to talk about gradient vectors in the context of level curves. Okay. Now let's suppose that I'm looking at a level curve. And do you guys remember what a level curve was? So a level curve was when you have your function and you set it equal to a constant. And the idea was that equation should describe some kind of a curve, all right? I guess just to be sure we're understanding what I'm talking about, I'll also make up an example as I go along. So let's say I have a function f of xy. I'm going to do something simple. I'm going to do y minus x squared for my function. And then I'm going to look at what happens if I set my function equal to 0. think of my function as the z coordinate. Okay? So in this particular example, my level curve is given by the equation y equals x squared. So that would be a parabola if I were to sketch it in the xy plane. Try to draw a picture. Okay. So that would be my level curve. Okay, is that good so far? Now, remember that when we were talking about curves, we usually represented them using a parameterization. All right? So let's suppose that I have some parameterization of this level curve. So I'll come up with an example, or I'll come up with one in my example. So if you guys remember, one strategy for coming up with a parameterization was to just make one of your variables equal to t, right? So let's say if I just let x equal t, since y is x squared, y would be t squared. Okay, so that's like one parameterization for our level curve right now. Okay. All right, makes sense? Okay. So in this example, notice that if I do f of r of t, oh, you know, I'm gonna be a little bit lazy. I'm not gonna write my vector signs. Okay. Okay. Anyway, so if you look at what f of r of t would equal, so if you plug in t and t squared for x and y, so you should get 0 when you plug it in, right? Okay. That's because this was a parameterization of my z equals 0 level curve. So in general, because this is a parameterization of this level curve, that means if I plug in r of t into my function, that it should be equal to this constant c, okay, from my equation. So what's going to happen is, looking at this equation that we have, if I do the derivative of both sides of my equation, okay? So over here, this was like our special case of the chain rule that we talked about before. So the derivative of this, according to the chain rule, it would be the gradient of f evaluated at this point, dot product with the derivative of r of t. So that was our special case of the chain rule just now. Whereas on the right-hand side, this is just the derivative of a constant. So that would just be 0, okay? So what we get is that this dot product of two vectors is equal to 0. And what did it mean when the dot product of two vectors was equal to 0? Yeah, what did that say about those two vectors? Yeah, okay, yes, they are orthogonal to each other. So, yeah, gradient. So you can roughly say gradient should be perpendicular to r prime, right? So then let me draw a picture of this. So let's say this is my curve. Let's say this is my point RT. Okay. So remember that r prime of t was supposed to be a tangent vector to the curve. Okay. So since the gradient is perpendicular to r prime, that means the gradient should be sticking out like this. And basically, the gradient is perpendicular to the curve itself at this point. Okay. So the main takeaway from what I'm showing you guys is that the gradient vector will be, well, I'll write it like this. So gradient vector at a point will be perpendicular to a level curve at this point, xy, okay? So that's the main takeaway. And then let me just try to illustrate with my example that I was building on this side. So our function was y minus x squared, right? So here's what I'm going to do. I'm just going to compute the gradient real quickly. So remember, gradient is the vector of partial derivatives. So the partial derivative with respect to x is negative 2x. Partial derivative with respect to y is 1. All right? Is that good? Okay. So let me look at this point 1, 1 on our level curve right now. Okay? And I'm going to plug in the point 1, 1 into the gradient. So if I do that, x is 1, so we're going to get negative 2. And this is still 1. All right? So I'm going to try to draw this gradient vector in my picture. Guess I'll do it in green. So I'm going to start at the point 1, 1. And then the vector negative 2, 1, I'm going to go out negative 2 and then up 1. So this green vector that I've just drawn, that would be the gradient vector at the point 1, 1. Okay? So it was negative 2 in the x direction, and then 1 in the y direction. All right? And as long as your picture is pretty good, which I think mine is, you can kind of see how the gradient is perpendicular to the parabola at that point. All right? All right, any questions about that? Okay. So then essentially the gradient is going to be perpendicular to level curves. That's what I wanted to show you with this example, all right? All right, any questions? All right. So I'm going to talk a little bit more about gradients. So first, I just want to recall when we talked about partial derivatives. So remember that the partial derivative of f with respect to x, this was representing the slope on the graph of f as you move in the positive x direction. So I talked about that before. I drew like a picture. I guess I'll draw a picture real quickly. So let's say if this is the graph of my function f of xy. And let's say I have this point x naught, y naught. And then here is the point right above it on the graph. Okay. So if you imagine walking along the graph in the positive x direction, passing through that point, all right? I indicated that the partial derivative of f, or I said that the partial of f with respect to x, at this point x naught, y naught, it was the slope on this curve, or if you will, slope of the graph at this point. Which is x naught, y naught, and the z coordinate would have been the function evaluated at this point, which we sometimes denote it as z naught, okay? But it was the slope of the graph at this point if you were moving in the positive x direction. Okay? And similar for the partial derivative of f with respect to y, it would be the slope at this point if you were moving in the positive y direction. Okay? Okay, so I want to talk about the slope if I were to move in another direction now. Okay? So let's say I want to find the slope of the graph at a certain point. In the direction of some other vector. Okay? So not necessarily in the positive x or positive y, but just in the direction of some other vector. Okay? Okay, so if we think about it, so to calculate the slope, I could try to do like all right, let me draw a picture first. So I'm just going to draw in the xy plane. So let's say here's my point xy. And let's say the vector v is pointing in this direction. Okay? So if I wanted to calculate the slope, so what we could do is calculate the change in z. And let me call this point P. So it's going to look nicer when I write it out. So I want to calculate the change in z over the change in position in order to get the slope, if you will, right? So I'm going to imagine that here I have the change in z between point P and some point in this direction. That's what P plus TB is representing, a point along this direction B. And then I want to divide by the change in my position, which in this case would have been T times the length of B. Okay? So that would be like the distance between my 2 points. All right? And in order to get the slope, I want to take the limit as t approaches 0. So I'm calculating like the slope at this point. All right? So this should be somewhat, if you guys remember, similar kind of to how we defined the slope in Cal 1 in terms of like the limit. Okay? Now, to simplify things, I'm going to choose v, this direction vector, to be unit length. Okay. So that just means that in my denominator, I can drop the length of v because it's just going to be equal to 1. So if I do that, this limit that we end up getting, so it's actually basically the definition of derivative that you guys learned from Cal 1. Specifically, this limit is actually just a derivative of the function f of p plus tv, that. Evaluated at t equals 0, because we were doing the limit as t approaches 0, okay? Oh, okay. Now, in order to compute this derivative, it's actually a chain rule situation. So if I use a chain rule, I would do the derivative of the outside function. Well, rather, this is a special case of the chain rule, so it's the gradient dot product with the derivative of the inside. Okay. Now notice derivative of the inside with respect to t would just be v. Okay. P is constant, v is constant, so it would just be v. And then if I evaluate at t equals 0, I will get the gradient of f evaluated at the point P dot product with V. Okay? All right. So this quantity here, we have a special name for it, the gradient of f at P dot product with V. We call this the directional derivative. So specifically, this is the directional derivative of the function f at the point P and in the direction of the vector v, okay? And so it's supposed to represent the slope. Or if you will, represent the rate of change. Of the function f at the point P and in the direction of the vector v. Okay? So that's the sort of interpretation of the directional derivative. And then I'm making note that the direction vector v has to be unit length for this to work. Okay? All right. So I'm just going to do just a quick example, computing a directional derivative. So let's say I have a function f of xy. Let's just do something like x squared times, I'll do e to the 2y. Okay? And let's say I want to find the, Let's say I want to find the rate of change of this function f at the point 1, 0. Let's say I want to find the rate of change in the direction 1, 2, and -2. Or actually, no, this is 2 variables. So I should just do 1 and, okay, it doesn't matter. I'll do 1 and 4. Okay? Okay, so to get this rate of change, I would just want to calculate the directional derivative. Okay? So notice that this question I can ask it a couple of different ways. I could ask what is the directional derivative of f at this point in this direction. That would be the same thing. I could also ask like what is the slope of the graph of f at this point in this direction. And again, that would actually be the exact same question. All right. So just kind of be wary. Question can be worded different ways, but they're all kind of the same thing. So this rate of change, I can calculate it by doing the gradient of f evaluated at my point. And then I would dot it with a direction vector, right? Now this is one thing that you need to keep in mind about these problems, the direction vector. Remember, it has to be unit length when you're doing this computation. Right now, the vector that we're given is actually not unit length, right? So if I look at the direction vector that we were given, what is the length of this vector? Sure, okay. So square root of 1 squared plus 4 squared, right? Okay. So it's not unit length. So if I want to get a vector pointing in the same direction but of unit length, what should I do? Right. So I want to use the direction vector 1 over root 17 and 4 over root 17 for my computation, all right? Okay, good. So then here we have the gradient of f evaluated at the point, and then dot product with my unit length direction vector. Okay. So let's just compute the gradient real quickly. So the gradient of f, so it's a vector of the partial derivatives. So the partial derivative with respect to x would be 2x e to the 2y. Partial derivative with respect to y would be 2x squared e to the 2y. All right, is that good? Okay. So I want to evaluate the gradient at the point that we were given, 1, 0. So we're going to get 2 and 2, okay? So then I would plug that into here as well. So it's going to be the vector 2, 2, dot product with this direction vector. And so it'll just be 2 over root 17. And then 2 times 4 will give me the 8 over root 17. So altogether, you could say it's 10 over root 17. Okay? All right, any questions about that? Okay. Then finally, in just the last minute or two, let's take a look at the directional derivative again, all right? So the directional derivative which remember represents like slope or rate of change. Okay. So the formula for it was gradient of f evaluated at our point, and then dot product with a unit direction vector. Okay, that was the formula. Now, remember there's a formula relating dot product to the angle between two vectors. So do you guys remember what that formula was? If I have a dot b, this was equal to the magnitude of a, or the length of a, times the length of b, and it was times the cosine of the angle between them. Okay? So I'm going to apply this formula to the directional derivative. So this would be equal to the magnitude of the gradient vector, then times the length of our direction vector. But remember that it's unit length, so it would be times 1, okay? And then it's times the cosine of the angle between the two of them, all right? So I'm just going to erase the times 1 now. So it's just this. Okay, so this represents the rate of change in f if we were at point P and moving in the direction of V. So looking at this expression, we end up getting the maximal rate of change at the point P. So in order for the rate of change to be as large as possible, I would need cosine of theta to be as large as possible, okay? So cosine was maximal when theta is equal to 0, in which case cosine of 0 would equal 1, okay? So the max rate of change at the point P occurs when theta equals 0, okay? Because then cosine, it takes on the largest value of 1. Now, if the angle is 0, what does that mean about my two vectors? I'm saying the angle between my two vectors was 0. So if that angle is 0, that means my vectors point in the same direction, right? So the max rate of change at the point P occurs in the direction of the gradient vector itself, okay? And then this actual maximum rate of change okay? Well, so when theta is 0, the cosine of theta was equal to 1. So the directional derivative would just equal the magnitude of the gradient. So that would be the actual rate of change at the point P in the direction of the gradient vector itself. And this is the largest or maximum possible rate of change, all right? So in other words, if you're standing on the graph at the point P, or above the point P, the largest slope on the graph would occur if you moved in the direction of the gradient vector. And the actual slope would be the length of the gradient vector, okay? And then very similar thing, if you want the minimum rate of change, at the point P. So that occurs when the directional derivative is minimal. And this will be minimal when cosine of theta takes on its smallest value, which is -1. Okay? So it occurs when theta equals pi, because then cosine of theta would be -1, so it would be the smallest possible value. If the angle between my two vectors is pi, that means they're in opposite direction of each other, if the angle is pi, okay? So the minimum rate of change, or the smallest slope, if you will, occurs in the direction of the negative of the gradient vector. Okay? And then the actual minimum rate of change, the actual value of this, is just going to be the negative of the length of the gradient. Okay? So the question asks you, like, in what direction will the function be increasing the fastest? That would be like in the direction of the gradient vector. If he asks you like the direction that it will be decreasing the most, that will be in the direction opposite the gradient vector instead. Okay? And then the actual maximum rate of change, if they ask for that, that would be given by the length of the gradient vector, and so forth. All right, so I'll end my review.